I guess it's recording now, yeah? So yes. Do you see me and do you hear me? If the answer to all these questions is positive, then I can proceed also. Okay, so let us start, and the topic of the lecture today is the connection between physical kinetics and hydrodynamics. Now, again, what I'm going to tell next kind of depends on you, and I need to know to proceed in a coherent way. I need to know what is your knowledge of classical hydrodynamics. Because today we're going to talk about the connection between physical kinetics and the classical hydrodynamics. So how many of you learn classical hydrodynamics?
I never studied it.
Okay, that's it. Okay, so so the lecture will be oriented towards people who have never learned classical hydrodynamics in their life, but just out of curiosity, how many of you ever learned classical hydrodynamics?
I had like a brief introduction of it.
Introduction, whatever, yeah.
Nothing too profound or deep.
Uh-huh. How about other people? Anybody else?
I've learned it, but when I was a bachelor student, so a long time ago.
That counts as learned. Okay, so 2 students learned, 1 student does not, and there's a group 1, 2, 3, 4, 5 students. So we have 1 student who didn't respond to the poll, and there is a sum in the chart that says just a few equations. Okay, so I guess some of you may have an ideas of classical hydrodynamics, some of you don't, and I'll try to talk in a form that approaches coherent for people who have never learned classical hydrodynamics. So I'll try to explain what I'm doing, why I'm doing, why it's interesting. Maybe it will go slowly, so it can take more than 1 lecture. So let's go slowly on this list. Why people, before we want to establish the connection between physical kinetics and physical hydrodynamics, why people are interested in hydrodynamics in general, and why we bother. Why do we need to bother? What is first of all, what is hydrodynamics? Yeah, in order to, before we even establish the connection.
Studying the flow of stuff.
Studying the flow of the stuff. Correct. Absolutely correct. The key thing here is what stuff.
Liquids.
And what else?
Particles. Like it could apply to the flow of electrons or stuff like that.
Flow of electrons. What else? Oh, another form, what is liquid? Let me ask you, what is liquid?
Denser than gas, but not ordered like solid. So not an actual structure to it.
What is the difference? What is the difference between gas and fluid? What is the critical density below which you can apply hydrodynamics, and what is the critical density above which you cannot, or vice versa? Where's the transition between something that cannot be studied within hydrodynamics?
I don't remember, and I don't have any clear intuition.
Answering this question will enable us to understand why we bother to establish this connection in the first place. Any other creative ideas from people who learn hydrodynamics? It doesn't matter in what circumstances and in what configurations. What was the point of learning hydrodynamics? And to what system it applies?
So you're asking what is liquid? Like
I'm asking no.
essentially.
I'm asking what is liquid from the hydrodynamic perspective. For me, liquid is anything that I can describe by hydrodynamic equations, and we will discuss what that means. But if I'll open a book that has the title Hydrodynamics on it, and I'm not teaching hydrodynamics right now, I'm only talking about hydrodynamics as something I'm gonna connect to. So there's a book and it has a word hydrodynamics in its title, what it will be about, what it can be about, and what it cannot be about. What is hydrodynamics? In a very broad sense.
Giving macroscopical properties to a collection of particles?
There will be a collection of particles, correct? There will be a collection of particles. What kind of particles?
Small agile particles.
Small compared to what?
To the space that they're occupying.
Okay, so
a box, something.
I will be looking at the system on scales much larger. So I will consider collection of particles, and here I would say any particles. Any particles considered or studied at scales, greater than, complete this sentence, greater than what?
Like size of particles?
So I have a particle size. Is this the criterion? Are electrons at the scale larger than the size of electron, whatever that means, can be treated as a fluid?
No.
No. So size of the particle is not the right scale. Of course, it definitely requires to be treated at the scale larger than size of particle. You cannot treat things hydrodynamic on the scales of the particle size, but that condition is not the right one.
Well, there are like other quantities like scattering length.
Scattering length. So let's focus on this. Scattering length. Why scattering length is important, and what scattering length are we talking about?
So if we are talking about, well, electrons.
Let's talk about electrons.
So we studied before that there is like elastic. So there are elastic processes and inelastic processes, okay. And there are different lengths, probably.
Yes. So what length will control when we have hydrodynamics, and why?
Maybe the elastic scattering length, because it will propagate through the get stuck together eventually.
So one version of the event, it's an elastic lens. Another version will be an elastic lens. What do we need to assume? What do we need to assume when we talk about hydrodynamics? What we need to assume about fluids? So there's some unknown length above which systems are described as a fluid. Now, what do we mean described by a fluid? So if we think about normal fluid like water, what would be the set of hydrodynamic equation? Let's start from another end. If we're going to write hydrodynamic equation, how many equations will be there and written for what quantities? I'm sorry, the connection seems to be unstable. Can you hear me right now?
Yeah, yes.
Yes.
Let me check that it's recording, but the screen is not sharing. Okay. So I'll be back in business. So those who took a course on hydrodynamics, what sort of equation do you remember? How many were they? And
well, I remember the continuity equation.
Continuity equation.
So
can you please repeat the question? Can't hear you well.
Okay, those who studied hydrodynamics, what do you remember? What equations do you remember? How many were they? Okay, did you hear the question?
Yes, I hear the question.
Okay, so the first equation was continuity equation. What did this equation tell us? In words.
That matter is preserved.
Correct. Number of particles is conserved. That was the continuity equation. That was its meaning. Number of particles, that was equation number one. What was the second equation?
I remember Navier-Stokes equation.
Correct. There was no equation.
So I think it's similar to Boltzmann equation.
Alina, they're all similar to Boltzmann equation. All three of them.
Okay.
They all follow the Boltzmann equation. But what Navier-Stokes equation tells us? What is conserved? All three of them are conservation equations.
I think energy is conserved. Like there is no friction, and like the flow is continuous or something like that.
The flow may or may not be with or without friction. That depends on the circumstances. But Navier-Stokes equation, it's always a conservation equation. And do you remember how it looked like?
I don't. I remember Bernoulli equation. I mean, I think I did something much simpler than this.
Okay. So what Navier-Stokes equation tells us? Paulina, do you remember Navier-Stokes? Okay.
Something like, so the full, so it's a conservation law, right? You said, okay, so maybe, maybe it's like full momentum or full energy. Yeah.
Full momentum. So there's a momentum conservation. So there is an equation called Navier-Stokes equation. Doesn't matter how it looks right now, but it has a physical meaning of the momentum conservation. It says that the momentum is conserved in the fluid as a whole. In the fluid as a whole, the momentum is conserved. And there was the last equation that you had to write for hydrodynamic.
Can you please write the equations?
I will write the equation eventually.
Okay.
I will write the equation eventually. Don't worry. But before going into the equation, let me just try to write schematically the meaning of this equation, and then I'll write the equation. Because I don't want to write the equation, because to write the equation I need to define new quantities, and I don't want to do that. And then was the last equation, as you might have guessed by now. The last equation has the equation that has a very simple meaning. It's an energy conservation. Yeah? And to describe all these, you describe fluid in terms of some variables. So when you talk about particle conservation, you formulate it in terms of density of particles. So you say that there is a number of particles, density of the particles at the point r at the time t, such that if you multiply it by the volume v, delta v, that would be an element of your fluid. Then this would be this is the element delta v. Then rho times delta v is a number of particles inside this box. So if you imagine a box of the size delta v and you have a density of particles rho of x and t, then this rho times delta v is the number of particles in this box. So there was one degree of freedom which we call density of particles. Then when we talk about momentum, we normally describe, we say that there is a velocity of the fluid. And if you multiply velocity of the fluid by the density of the fluid, you got the momentum density. So this is the velocity of the fluid. Velocity of the fluid.
You have I think there is a sound problem because I hear you FF.
Sound problem.
Maybe it's connection.
It's definitely connection, but I'm not sure if I can do anything about it because I'm in my office. Hi, let me see if I have a cable connection. I'm supposed to have a cable connection. Yes, I have a cable connection. Everything is connected. That is as good as it can possibly be. Look, I can teach this class in a seminar room if you will come. I'm physically here, so if you come to university, we can just go to the seminar room in the Resnick building and teach it and talk about it in the normal environment. Or in my room, I think it's only 5 people. We can. So whoever wants can come to my office and join me, and then there'll be. I don't know any other solutions. Okay, so V is the velocity of the fluid, and rho, like I said, is the density. Rho is the density of the fluid. It's a particle density. It's a number density, particle density of the fluid. So we have a particle density, we have a momentum density. Sometimes we use velocity of the fluid as a variable, but it's related to the momentum density. And finally, we have a variable which we call energy density. of the fluid. And these are 3 degrees of, these are the only 3 variables that suffice to fully describe the flow of the fluid. And now the question is, why these 3 variables suffice? What's special about these 3 variables, and what one needs to assume about particles in order to use these 3 variables to describe this many-body system? And this is the key thing as far as we are concerned. Why only 3 quantities all of a sudden are sufficient to describe the flow of particles, and under what conditions they are sufficient?
Well, I think, like, as we were talking about conservation laws, so the only integrals of motion are like the full energy, the full momentum, and number of particles. There is nothing else which is conserved. So that's why probably.
That's correct. That's a good point. So these are 3 conserved quantities. These are 3 conserved quantities. But like you said, Polina, the full energy, full density, and full momentum, so to say, let me rephrase it better. The full energy, the full number of particles, and the full momentum are conserved. So the momentum of the entire system, the number of particles of the entire system, and the energy of the entire system are conserved. So why are we talking about energy density, particle density, and momentum density?
Because we want to see the distribution inside of the fluid?
Yes, but why these 3 things why is it possible to write a set of equation, a closed set of equation in terms of these variables that describe the fluid? We have a system of millions, billions, gazillions of particles flowing. And normally when you're solving many body problem, you cannot describe in terms of, I don't know, three classical fields. So what happens here, then all of a sudden you have a very complex non-equilibrium problem, and you are able to describe it in terms of a very limited number of variables.
The particle symmetry, maybe?
What is the symmetry in the water that flows through the pipe?
Each molecule is like this, like each particle is the same as the particle before it. No?
Yeah, lots of particles. Not necessarily identical.
But like we are not interested in microscopics, so on this like large scales we discussed before, so we can like describe a fluid as a like kind of single object.
It's the scale remains unspecified. So we obviously want to describe this system on some scale which is large enough. But what controls this scale, and why? Why can we describe something on the scales larger than something by 3 classical variables, not 4, not 5, not 1? Remains a mystery. There is something that happens within these particles, something that happens between these particles that allows us to describe it by 3 degrees of freedom.
Is it connected to time symmetry?
No, it's absolutely unrelated to time symmetry. The fluid can be time reversal symmetric or time reversal asymmetric. You can study a motion in the magnetic field. You can study hydrodynamics in the presence of magnetic field. Our friends from astrophysics do it all the time. And in their case, the constituents of fluid are stars. So the zillions of stars that flow through the galaxy, and there are galaxies of stars that flow through the universe, and they describe the motion of these galaxies using the equation of hydrodynamics. So hydrodynamics is something that occurs at absolutely totally different special scales for some system. These scales are nanometers, and some systems, these scales are millions of miles, but there is some equivalence, some physical mathematical equivalence in the way stars behave at sufficiently long distances as electrons behave at sufficiently long distances. Long being totally different in each and every case.
You mean the interaction of the particles are larger than the small forces of the particle itself?
So yes, it has something to do with the interaction between particles. Now, why the interaction between particles is so important and what this interaction is doing?
Well, each particle makes the other particles around it flow in.
The particle, whatever it is, collides with other particle in whatever way it wants. Schematically, there's a schematically scattering process that may involve an unknown number of particles, and what is the outcome? What is the outcome of this scattering process that enables us to use the hydrodynamic description? That's the foundation of any hydrodynamic theory. And this may be star-star collision, it may be electron-electron collision, it may be molecule of water colliding with another molecule of water. There is some collision process with some diagram describing it. Why this collision enable us to think about this system hydrodynamically? Try to figure it out.
Since it's elastic?
Say it louder.
It's because it's elastic?
What would happen in the elastic collisions? We all know it by now. Take electrons, put them in the disordered metal. Yeah? Think about electrons placed in the disordered metal, such that there's lots of elastic collision. Would this system be ever described by hydrodynamic equations?
Okay.
Yeah, we know it's not, yeah?
Maybe it's related to the fact that when we talked about collisions in static disorder, after every collision, it's like a new process of scattering. And here maybe we count for the previous collisions in each iteration.
So there are many processes of scattering, and then what?
Like it's just a guess, but maybe after a collision, the particle has a certain state which affects the next collision, unlike other cases when we forget our state after every collision.
Okay, forget the state that we had before the collision, and what state? That's partly true. And what state are we approaching? So we could have started in a very complicated state, that's true. Then as the collision happened, we forget about our initial state. So we could have started in the state which was a highly entangled state with a very complicated, I don't know, density matrix or wave function. And then there are lots of collisions. What state are we approaching?
equilibrium?
Equilibrium. We're necessarily approaching equilibrium. And now, so with this understanding in mind, what is the so we go back at the beginning of our lecture. Sorry, that was a different lecture. So here, when we say that collisions of any particle, so we can hydrodynamically look at the collection of any particle considered scales greater than what?
Then the collision length, like
The collision length. What collision? That all
the distance between the distance which a particle is moved until it collides with another particle.
So it's a collision length. Yes, it's L. But what collision length do we have now in mind? What are collision lengths?
Maybe it's very small.
The smallest collision length. Sorry, there is some thing in the chart. Just a sec. Here. Mean free pass, yeah, but remember we have more than one mean free pass.
Well, inelastic, as you just wrote.
But what inelastic? So let us look back at the equation. So we have a set of equations that tells us that there is an inelastic collision that is responsible to energy relaxation. There is an elastic collision responsible to momentum relaxation, and so on. So what happens at this length scale? So what happens as a result of all this inelastic collision? What happens as a result of all this inelastic collision is what is called local equilibrium. So we all know that if there are sufficiently many inelastic collisions in the system reaches the state of ultimate thermal equilibrium. So it means that the system will be distributed in accordance with, I don't know, some Fermi Dirac distribution function or Bose-Einstein distribution function with a given value of chemical potential, temperature, and boost velocity. This is what will happen if you take any system with an elastic collision, put it in a box and wait for infinity. Now, before you wait to infinity, there is some transition. And transition is that system reaches the thermal equilibrium locally. So you have a box roughly of the size of inelastic collision. And for simplicity, let's think that all inelastic lengths are the same. So there is a box in which energy of the particles have equilibrated. So there's an energy exchange, and it occurred sufficiently many times on this length scale. Then there's a momentum exchange, and it occurred sufficiently many times on this scale, and so on. And so what it means that if you look on this box, then within this box, the system has reached a thermal equilibrium. It's called a local thermal equilibrium. Now, what is the typical size of this inelastic lens? Is system dependent. So it can be, so this inelastic lens can be of the order of nanometers for molecules. Or it can be 10 into, I don't know, 10 meters for stars. But that there is a scale if particles interact. There will be always a scale at which they exchange their momentum, they exchange their energy. And this is the scale at which hydrodynamic description starts to work. So we can only apply hydrodynamic theory beyond this scale. And the type of particles, the type of the consistencies of the fluid play only the role in establishing this scale. Beyond the scale, all systems look identical and are described by practically the same set of equations. This couple of footnotes to be added to this, but that's the main idea. And that's why hydrodynamic description is so universal. You can.
Wait, I didn't quite get it. What is special about this scale? Can you repeat, please? Sorry.
So the scales that control the transition to hydrodynamics, it's the scale of an elastic scattering. The scale, so for example, there is when we talked about electron scattering, we noticed that the energy is not conserved. Sorry, energy of an electron. Not conserved in the process.
It's hydrodynamics when all collisions don't pass energy from particle to particle.
No. Let me say it again. Energy is not conserved in the process of electron collision. So we have an electron. Then we have another electron. They collide. So there's process of two particle collision. Two electrons coming in, two electrons going out. We discussed this process last time. This process has a length scale and it has a time scale. So we have computed the process of electron scattering rate last time, if you remember. We can attribute to this a corresponding length scale. Huh? So there is an electron length scale, which is V Fermi tau E. It's a length scales at which particles collide. We can also compute the scale of their electron energy relaxation. So this is more or less the length scale at which energy is being equilibrated. Do you have a question?
Okay, so what is the definition for the hydrodynamic?
What is what?
So transferring from this to hydrodynamics, what is the difference? Like what is what happens when we scale up to the hydrodynamics?
So how do we go to hydrodynamics? Yeah.
Yeah. What is different in the hydrodynamics collision?
What is different in hydrodynamic collision? So it's not there is a difference in hydrodynamic collision. Hydrodynamics applies at the scale above inelastic scattering lengths.
Okay.
Now, how does it work? So let us start thinking in terms of Boltzmann equation. How can we derive a Boltzmann equation how can we derive a hydrodynamic equation from the Boltzmann equation? Now, the key thing here is to look at the collision integral. So what is special in the collision integral? If we consider system at distances longer than inelastic length, what can we tell about the Boltzmann equation if we look at the system at scales beyond inelastic length? What is the biggest part of this equation? What is the smallest part of this equation?
Well, I think in this case, the right hand, the collision integral is small. Well, is small. So
if you look,
if you're at large scales,
look at scales much larger than an elastic length. Is this what you are saying?
Yeah.
Why? Where the collision integral is important and where it's not. If I have a system, I have some typical particle collision rate. Where the collision integral will be important.
Well, I just remembered that the collision integral, so there is a scattering amplitude and it scales like 1 over tau. So
collision integral in the crudest possible approximation is just a function minus equilibrium distribution function divided by some some relaxation time. So where this integral will be important? It's the very crude approximation.
So you mean at which time scales or lengths?
All lengths we can translate.
So yeah. So when So when we are like far from F0 from equilibrium, so when times are smaller than tau this the scattering time.
Let us study this question, time scales. Let's only keep these two terms in the equation. df over dt is equal to f minus f0 divided by tau. Can we solve this equation?
Yes, so it will be exponent. So f0 times exponent.
Okay, it probably should be a minus in here. Correct?
Yeah.
So at what scales collisions change the distribution function? At what time scales they change the distribution function?
Then at time scales larger than tau.
Correct. So for times smaller than tau, we can essentially ignore collisions. For times longer than tau, collisions are very important. Actually here, just a second, let me solve it properly. Let me solve it properly. So I have let's solve this equation properly. It's equation, it's a linear equation, so it has it needs, so let's solve the general solution of so there is homogeneous part and a general solution f of t is a e in the power t over tau. Correct, that's the general solution of this. And there is also, we need to find a solution of non-homogeneous equation, and the specific solution will be f0. So altogether the equation has a solution which is f0 plus a e minus t divided by tau. And okay, so if we start, if we know that at t equals 0, the distribution function f at t equals 0 is given. And okay, so f0, this will, let me write as f equilibrium, just not to be confused. Then f of t should be equal to f equilibrium plus a e minus t divided by tau at time equals 0. This is equal to f equilibrium plus a. From here, a is equal to f at t equals 0 minus f equilibrium. So it means that f of t is equal to f equilibrium plus f at t equals 0 minus f equilibrium times e minus t over tau. Such that for t equals 0, we are getting that it's equal f of t equals 0, whatever it is. And for t goes to infinity, this thing approaches f equilibrium. So we start with a function f, which is whatever, and then at a scale tau, this typical scale tau, approach equilibrium solution. Now, of course, this is a function of momentum, but this is so essentially what we are saying, that distribution function as a function of the momentum and time, it's an equilibrium function. of energy plus f of 0 and p minus f of epsilon p equilibrium times 1 minus t over tau p. That's a refined version of this equation. So it says that at each and every momentum, at each and every energy, the system approaches its equilibrium value with a typical rate tau p. And it means that we can, the conclusion from here, we can ignore the collisions for times shorter than tau. What it also means that at times much greater than tau, the distribution function f of p approaches equilibrium distribution function. Do you see it? You either see it or don't. If you don't, I can.
Yeah, it's clear.
Is it clear for everyone? People, if it's not clear, is anyone who it's not clear for him and wants to ask a question? Okay. If not, can you now rephrase this thing in terms of length scales? If you understand the time scales, let us rephrase the same story in terms of length scale. So what happens to the distribution function at scales below inelastic length, and what happens to distribution function at scales beyond inelastic length?
Well, it's like with time. So if we're at very short scales, then we can ignore collisions.
What for lengths shorter than L inelastic, ignore collisions. What happens there? We have no idea because it depends on the distribution you have created. So it can be any distribution function as a function of momentum R and T. And they are all perfectly legitimate. You act with some forces on the system, you create a distribution of particles. And then for each and every problem, you may have your own special distribution function. What happens for scales, for lengths longer than an elastic? What can we tell about scales longer than special scales longer than an elastic?
Well, at these scales, the distribution function approaches the equilibrium.
Correct.
Level.
So for these scales, f of p, r, and t must approach f equilibrium. And now we know that there's only one equilibrium function, correct? It's called, so it's fully determined by statistics of particles. So if we're dealing with fermions, it will be Fermi-Dirac function. If we're dealing with bosons, it will be Bose-Einstein function. But let's say that we're dealing with fermions, it means that the distribution function, it's only the function of energy. So this is much narrow set of functions that the function that we started with. So we started with all possible distributions described by function fp of r and t These were the objects. These were the objects describable within Boltzmann kinetic equation theory, or within kinetic equation theory. And what inelastic collisions do, they severely reduce the Hilbert space of the problem. They project all distribution function on a very narrow manifold, so to say, of functions that are, well, functions that are equilibrium distribution function. So this guy do we agree? Disagree?
Yeah, it's clear.
Yep.
Okay, so if this is clear, let me ask you, how on earth will be able to have densities and energy density and momentum density that depends on the coordinate and time? If everything is at equilibrium, where the time dependence, spatial dependence will come from? What is the density of particles? If suppose I know the distribution function, yeah, as a function of energy, what is the particle density at the point r and time t? How do I get it from distribution function? You must know it by now. What do I need to do?
You need to integrate F over P.
Correct. So I integrate it with respect to P, F Fermi Dirac epsilon P. How come that I end up having some R and T dependence? Why I'm not just getting a constant?
Well, the energy has a connection to T and R, maybe.
Energy has correction that is R.
Energy depends on T, like energy is an equation.
Well, there are some systems where that happens, but it can be, but there's something much more simple here than position-dependent energy. Position-dependent energy may occur, but what is not fully fixed? What is not completely fixed? What are degrees of freedom that remain to be not uniquely determined when we said that the distribution function has a form of Fermi-Dirac distribution function? What can I change?
So in the distribution function itself, you have this energy, so it depends on velocity. So you're asking, so why?
Why I'm not getting here a constant?
Independent on time, right?
Correct.
Okay, because you have, yeah, like you have in your distribution function, you have energy, so it's like one particle energy, p squared over 2m, and you have equations of motion. Well, I mean, like momentum of like P can depend on time, like momentum of a particle, I guess. No?
In this way of thinking, the momentum of a particle is just a place in the phase space. It's a coordinate in the phase space, yeah? So you have a phase space and there's a point P and point R there. What was not fixed? What is there? Remaining degrees of freedom that allow
chemical potential?
Chemical potential.
The only thing.
So what may happen? What may happen to the chemical potential? What it can be? What can we do with the chemical potential and why?
Can move it?
Yes, we can move it as a function of R and T. So what happens? What happens if we slowly change chemical potential? What happens if we slowly change chemical potential so that we have some local collisions? So think about it. What chemical potential does in the problem? What it controls? So if you change chemical potential from one value into another, what it changes? Roughly in the first crudest approximation.
The Fermi level.
Well, and what does this do?
Number of particles.
Number of particles. So chemical potential, roughly speaking, very roughly speaking, controls the number of particles. So now you can have a system which is at equilibrium locally with one value of chemical potential. Or you can have a system which is at equilibrium with another value of chemical potential. Now, mind you, collisions occur locally. Collisions among electrons occur locally. So locally in space. What this means, it means that collision integral is something which is local in space. It means that if you plug into collision integral something which is Fermi Dirac function epsilon p minus nu1 over t, it is 0 as much as well if you put there distribution functions with chemical potential 2. Whatever value of the chemical potential you put in, this distribution function still nullifies the collision integral. Because collision integral does not care what is the value of chemical potential. Anything that is at equilibrium with whatever value of chemical potential is a zero mode of collision integral. That's an important realization. So that means that if I allow to change chemical potential slowly in time, same time, but you can say the same things in space, then when I go back to the Boltzmann equation that we used somewhere at the beginning, I probably already erased it. Here it is. So when I use the Boltzmann equation at scales, so I'm now going to look at the Boltzmann equation at scales greater than an elastic collision length. When I look at these scales, my first and natural suggestion is to replace distribution function by Fermi-Dirac distribution function. And if I do that, I approximately solve Boltzmann equation, because the biggest term in this Boltzmann equation at the long scales is a collision integral. Everything else is small corrections. Or if you want to say, if it's more convenient, we can look at this in time domain. So we see from here that in the long time, the collision integral is the dominant part in the Boltzmann equation. So at times longer than the scattering, than an elastic scattering time, I should be using the Fermi-Dirac distribution function as a zero order solution of the Boltzmann equation. However, nobody told me what is the value of chemical potential that stands there. And the point is that I can smoothly change, slowly change the value of chemical potential in time without causing too much trouble. Therefore, the value of chemical potential was not fully fixed yet, and I can change it slowly, whatever slowly means, without causing too much trouble. What else is not fixed? What
temperature?
Temperature, of course. I can also change temperature because collision integral does not care what temperature the system is. As soon as it has a thermal distribution function with whatever temperature, collision integral will be nullified happily. It does not know, once again, it's a local scattering process. It doesn't care if the temperature in this region is not the same as the temperature in some other region. As soon as here there is a local thermal equilibrium with some temperature, the collision integral is gone. Therefore, I can slowly change temperature in space and time without involving excitations that are energetic. So mind you, we're moving in the right direction because change of the chemical potential sounds like the change of the particle number. So change of the temperature more or less sounds like the change of a local energy. And we need one last remaining degree of freedom, which is the local momentum, yeah? Local velocity. Where is that coming from? And that is coming from Galilean invariance, meaning that if you have a spectrum epsilon of P, whatever it is, in the reference frame which is boosted with respect to this frame with some velocity V, the distribution will be like this. So the energy in this is the energy of the particle with the momentum P in the reference frame that is moving with respect with the velocity V with respect to our original reference frame. Yeah. So if we go in the reference in one reference frame, there was a momentum P, and the particle had energy epsilon P. Then there is a moving reference frame that moves with the velocity V, capital, with respect to the original reference frame. And in this reference frame, the energy will be epsilon P plus V times P. This is the energy in the moving energy, in the moving reference frame. But now if there is a Galilean invariance, it means that fluid, it means that the fluid is everywhere. That it means that the Newton law are satisfied in the moving reference frame. Then it means that the collision integral will also vanish, will also vanish after the distribution function is being shifted from one reference frame to another. This will be also zero in the moving reference frame. So if there is no collision, if there is no thermal relaxation in the standing in the reference frame that which is not moving, there will be no collisions in the reference frame that is moving. And we end up having 3 degrees of freedom: V, R on T, nu, R on T, and temperature R on T, that we can change slowly without changing the collision integral much. And these 3 are the only 3 quantities that have this property in the most general situation. They all must obey this. All collision integrals must obey this condition, because all collision integrals conserve the energy of particles involved in the collision, number of particles involved in the collision, and the total momentum of particles involved in the collision. So this is the most robust properties that are satisfied in the process of practically any collision. And if they do, it gives rise to 3 slow modes of the Boltzmann equation: velocity, chemical potential, and temperature. And these are 3 modes of hydrodynamics. Did you follow the logic?
Think so. Can you repeat the last 2 sentences?
So we realized that we can change 3 parameters. We realized that collision integral is nullified by any function that has a form of Fermi-Dirac distribution function. We also noticed that in the Fermi-Dirac distribution function, there are 3 parameters that are left alone. So Fermi-Dirac distribution function is any function that looks like this. There are 3 parameters: V, nu, and T. 3 constants, yeah? So I can choose whatever value of these constants I want, and collision integral acting on Fermi-Dirac distribution function with this constant will be still equal to 0. It means that I have 3 fields that I can change, and these will be 3 low energy modes of the effective theory that describes particles with inelastic collisions in the long time limit, long compared to the inelastic time scales, and special scale compared to inelastic length scale. Now, when I look at these 3 modes, I can relate these 3 quantities. I can relate these 3 quantities to the particle number conservation, momentum conservation, and energy conservation. And these would be our favorite hydrodynamic degrees of freedom. Did you follow the last sentence?
Yes. Yes, yes.
Okay, so we now see where 3 degrees of freedom are coming from. We now understand why these are 3 degrees of freedom and not 4 or 5. And now we know how to get them. So let us start now deriving the kinetic equation. So what have we learned? We learned that more formally that if we have, say, electron collision integral acting on the distribution function f, it conserves the total number of particles, which means that if we integrate this thing with respect to all momentum, that has a meaning of the change of the total number of particles due to inelastic collisions. And this is equal to what is it equal to?
Well, it should be 0.
Should be 0. It's better to be 0. Now let's see what do we know. So let's take the same integral, multiply by momentum, and integrate with respect to dCp. What is this thing? It's a change of the total momentum of the particles as a result of an elastic collision. What this integral is equal to? What can we tell about this integral?
So it's a change of momentum due to inelastic collisions, right?
Total momentum of the electrons due to inelastic collisions. So electrons collide. Each electron changes its momentum. This is the total change of the momentum of all electrons that are locally at the point R at the time t. And scatterings are local in space.
I think it should be also 0.
And the last thing, this is the change of the local or total energy of the particles. What is this integral?
This is also 0.
This is also 0. So these are 3 conserved quantities of the electron scattering processes. These are three conserved quantities that will allow us to write equation of motion in terms of particle conservation, momentum conservation, and energy conservation. Now, if I would ask you, why couldn't I write a hydrodynamic set of equations for electron disorder scattering? Or could I write the hydrodynamic set of equations for electrons and static disorder? Would that be possible?
So assuming that, so the scattering is elastic or, okay, inelastic, right?
Electron and
so inelastic scattering, so we have inelastic scattering between electrons and disorder, right?
No, you cannot have inelastic scattering between electron and disorder because energy is conserved.
Oh, okay. So it's elastic scattering.
Correct. Yes.
But then like, I think we have a problem because then the, we never reach this equilibrium which is necessary for the hydrodynamics.
Correct. So let me just draw you an example, yeah? Let me draw a distribution function as a function of energy. So instead of Fermi-Dirac distribution function, let me draw this and then this. So there are states there, and no electrons in between. So what would happen if I place such distribution in the disordered metal with no interaction? Now there's no inelastic collision, so it means that the distribution at each energy shell don't talk to distribution on other energy shells. So it means that this hole in the middle will never be cured. Electrons will never relax and form a distribution function that has a Fermi-Dirac form. Yeah? So this is the Fermi-Dirac form for finite temperature. This is the Fermi-Dirac point, but it never has this inverse population form. Yeah? And if you have only elastic scattering, then this function will never approach thermal equilibrium, which means that we will never be able to reach the hydrodynamic regime. What about electron-phonon interaction? What is conserved for electron-phonon interaction? What can we say about electron-phonon collision integral? Is this zero? In other words, is the total density of electrons is changed by electron-phonon scattering?
Local density of electrons? No. No.
So does it?
Wait. Local.
Imagine that the scattering between electrons and phonons are local, which is roughly correct at some special scale. So if you have an electron phonon scattering, would it change the total density of electrons at that point?
I think yes.
Where would they go? Where would they go?
I'm just thinking like, okay, if you, well, because you, if you create a phonon, say,
Yeah.
So what is phonon? Phonon is a, like, yeah, so when, okay, maybe I'm wrong. So
you have an electron is coming in. Then maybe 2 electrons are coming in. That's not important. You have an electron coming in. That these electrons emits a phonon and changes its momentum. So it was coming with the momentum P. It emits phonon with the momentum Q. Now you have an electron with momentum P minus Q. Did you change the total number of electrons at this point?
No.
No. So it means that the number of electrons at this point is conserved. So this integral is 0.
Okay.
What about the integral times P? Did you keep the momentum of electrons conserved?
Locally not.
Not. Even globally not. You only kept the total momentum of electrons and phonons together.
Yeah.
But if you look at electrons, then you have changed the momentum of electrons. What about the energy of electrons?
Also not 0.
So the only conserved quantity is, in this case, is the number of electrons. Now, will the system reach the thermal equilibrium if you have only electron-phonon interaction?
Yes.
Correct. What can we tell about this thermal equilibrium? What will be fixed in this thermal equilibrium?
I think temperature.
Can we change temperature?
No.
Because now this temperature is fixed by phonons, so this temperature will be equal to the temperature of phonons. Can we change chemical potential?
Yes.
Yes. Because the total number of particles is conserved. Can we boost velocity by transformation?
Yes.
No, because we have a preferred reference frame, which is the reference frame of the solid. If you mind you, the total momentum is no longer conserved.
So you kind of broke Galilean invariance by.
I broke everything by lattice.
By having.
Lattice. So now so the conclusion is that in the case of electron-phonon interaction, system goes towards thermal equilibrium, but would be only 1 degree of freedom. That it remains alive there, and this is the chemical potential. So this will be also, in some sense, hydrodynamic description, But this will be a hydrodynamic description that only involves one field, density of particles or chemical potential of the particles. That's the only degree of freedom that you can change in this system. So the conclusion that follows from it, that standard hydrodynamics with three conserved quantities corresponds to the system which is closed. So we need to have a closed system, like electrons, such that the energy, momentum, and particle number are conserved. In this case, we will now derive hydrodynamic equation from kinetic, and we can set that there will be three variables that we are interested in. Variable which is density, variable which is a momentum density, and variable which is an energy density. And this will be our conserved charges of the hydrodynamic theories. Okay, I think I explained logic. Let me start doing derivation in 1 week from today, because I don't want to stop in the middle. So let us stop now. And if you have any questions, you're welcome to ask.
So like it's maybe a stupid question, but so so in case of when we have electrons and phonons and electron-phonon scattering, so the only quantity which is not fixed is mu, right? Chemical potential. And we can write the hydrodynamic equations for this chemical potential, but is there any example where it's also like, where, for example, the chemical potential is fixed and temperature is not, for example? And what, like in general, what tells me how many
degrees of freedom?
Yeah.
Well, these are very good questions. So how about the second one? What tells you how many degrees of freedom are conserved? I think the second question is, I think the first question is a part of the second one. So let us address the second one. So what tells us how many degrees of freedom are conserved? And if by any chance there's more than these three, where these things are coming from?
Well, like all the conservation laws, they follow from symmetries. So maybe we can imagine a situation when we have spin degrees of freedom, then we will have additional conservation laws. So
Precisely.
That's it, I guess.
Precisely. So the conservation laws I wrote assumes that all other symmetries are broken. So this, if you want, these are ultimate conservation laws that exist in any system left alone at sufficiently long scales. So if you start with any system left alone, or in scientific words, thermally isolated from the environment, doesn't matter if the system is made of electrons or stars or water molecules, then at sufficiently long scale, it must reach this universality class because these three conservation laws are always there, assuming that all other symmetries are broken. So if system is thermally non-isolated, that as you saw from the example of phonons, then even these degrees of freedom are violated. But assume that the system is thermally isolated from the outside. So you have stars that collide with other stars, and there is nothing in the universe by stars and other stars if you look at the universe from sufficiently big scales. But what if there are other conservation laws? What if there are other symmetries? For example, the one that you mentioned, some spin in the system, and then you will have some conservation laws that correspond to the rotation of spins. And God only knows how many symmetries you may have. What will happen in this case, Polina? On a qualitative level, not on the quantitative level. What will happen then?
Like, what do you mean? Can you explain once again?
Where this information will be encoded and how it will change the equations of hydrodynamics.
So you're asking, okay, if I have like more symmetries?
Yes, you have more symmetries, you have
degrees
of freedom that are conserved.
Okay, so then I will have like additional equations similar to continuity equation, for example. Like okay, all dictated by Noether theorem and.
Yeah, so imagine you have some spin conservation, then in addition to the particle density, you will have some spin density, yeah?
Mm-hmm. Yep.
And then somebody tells you that these spins are conserved. Spin is a conserved quantity, and therefore that will be a conserved spin density, and will be a spin density current, a spin current, yeah? A spin current which is associated with spin density. So in addition to the particle conservation, you will have a spin conservation equation. So what would mean that now distribution function will not only be function of PR and T, it will be function of PR, T, and some spin index, I imagine, yeah? And then you will have some features of the collision integral. That collision integral conserves, I don't know, energy for each and every component of the spin. So you don't sum the full energy, but you only sum the energy of particles with a certain projection of a spin, and that's good enough, and this thing is conserved. Yeah? I'm just imagining it. So in this case, you end up in having hydrodynamics with a larger number of conserved quantities, which is called multi. In this case, you will have multi-component hydrodynamics. So more symmetries, more conserved charges, quantities, and then you will have multi-component hydrodynamics.
And then I will have so I will have like two different distribution function, one for spin up, the second one for spin down, and each with own temperatures, chemical potential, and boost velocities.
And in this case, you will have 6-component hydrodynamics.
Okay, so if I want then to write then I will have to write 6 equations for all these quantities.
Mm-hmm.
Okay, and so I will just substitute this ansatz to we used before to all this conservation law.
I haven't shown you yet how you derive hydrodynamic equations from Boltzmann equation, but you will end up having 6 different hydrodynamic equations, very similar to the standard hydrodynamic equation, but each one for its component of spin projection. The difference, though, that these conservation laws will be approximately an approximate conservation laws, not like a true hydrodynamic equation. This conservation law will only hold as long as there is a spin separation in the problem, as long as the symmetry that preserves the conservation of each individual component of the spin holds. Yeah. So either you tune your system to a very high symmetry fixed point, or it's just some approximation that breaks down at some sufficiently long spatial scale. But nevertheless, you will now have a hierarchy of hydrodynamic regimes where on the short scale, you establish a thermal equilibrium within some multi-component hydrodynamic regime. And then as you increase the scale, there are fewer and fewer hydrodynamic modes survive till eventually you reach the universality fixed point of 3-mode hydrodynamics. And this is the hydrodynamic theory that is normally explained in the textbook.
Okay, you're saying that, so I have 6 equations, but they are decoupled, like 3 and 3, something like that.
Decoupled, they are approximately decoupled, but there is an approximation there. There is some small term that you neglected that couples, because the conservation of individual components of the spin is not a law of nature. It's just some property of your collision integral that you computed, I don't know, within some second Born approximation or fifth Born approximation, God only knows what, but that may be parametrically good, but that's not exact. As opposed to the energy conservation, which is quote unquote exact, provided that you manage to isolate your system from the environment, which is also never the case, yeah?
Okay.
But at least there is this kind of hierarchy that you need to keep in mind. So standard books on hydrodynamics imply that there's no conservation law besides these 3 ones. Additional conservation laws lead to multi-mode hydrodynamics, by the way, very popular subject these days, especially in the context of electronic hydrodynamics. Electronic hydrodynamics, hydrodynamic that is observed in clean metals and semiconductors, typically have multi-component regimes, which makes them very special and very interesting.
Yeah, so may I ask the last question? So imagine that spin is not conserved. So the only equations I have is the 3 that we wrote, but I know that particles have spin. So then I kind of have 3 equations for 6 quantities. Is it true?
No,
so what, like?
It's a wrong way to think about it. You have 3 equations for millions of quantities. You started with the many body problem that can be only described in terms of highly multidimensional Hilbert space. Yeah, you have a many body problem with 2 in the power n degrees of freedom needed to describe it. Then due to the thermalization, due to the inelastic collisions, you have thermalized this problem. It means that a very complicated density matrix, which lives in a highly dimensional Hilbert space, is reduced to much poorer and very narrow manifold that is parameterized by 3 or 6 components. That's not that important, by a finite number of modes, low energy modes. So after thermalization, a many body problem, which is quantum mechanical problem in a highly dimensional Hilbert space, is reduced to the classical problem in a much lower, in a finite dimensional Hilbert space, or much lower dimensional Hilbert space.
So, okay. Mm-hmm. So you're saying, like, imagine I have a like Hamiltonian, which is which breaks all the SU2 symmetry, like, I don't know, Ising Hamiltonian or something like that, or I place electrons to magnetic field.
Hamiltonian is not good enough because that's an exactly integrable Hamiltonian, and that means that you will not have a normal thermalization. You will be in, as long as you're near exact integrability point, you will be in this problematic situation when there's no thermalization. Yeah. You need integrability by yeah.
Okay, so if I break integrability, then I will reach the regime where the spin degrees of freedom will be decoupled.
Yes. First, then you will reach the regime where everything will be coupled. If you stay close to the exactly integrability point, that will be another very popular subject of these days. And I forget how it's called. It's enormously popular, and like half of the papers on arXiv roughly on this subject, but I forget. Now I remember, generalized hydrodynamics. So what you do when you're close to the integrability point, and then you have next to the infinitely many conserved quantities, how do you write sets of hydrodynamic equations if you have nearly infinite number of conserved quantities?
Mm-hmm. Mm-hmm.
Yeah, that will be
okay.
Next to the integrability point. But let's try to understand simple-minded classical hydrodynamics. This possible extension towards the multimode hydrodynamics, that's very close, though a bit extending of that thing. Okay, people. So the plan for the next lecture is to start from Boltzmann equation and derive properly the three famous hydrodynamic equations of classical hydrodynamics. See you next week.
Just telling everyone who's not in the WhatsApp group may join, just so you know.
What wasn't in the Dropbox?
No, I told the other students that if they want to join a WhatsApp group, they can message us and join.
There is a WhatsApp group to discuss things. Okay, sure. And
just told the other students because not everybody are there.
By the way, if you want to meet in a normal seminar room, just let me know and we can organize normal meetings in seminar room or in my room or whatever.
If it's possible to have a normal seminar where it will also be recorded, so we can enjoy both the recordings and both the.
I can ask our secretary if they have enough rooms by now to have everything at the same time recorded. And to stay in both worlds, a virtual one and a real one, that's fine.
Okay.
I just noticed that it's very hard for me to talk without seeing the audience, and it's also very hard for me because the connection is not very stable. So it's obviously difficult for you to listen as well. So that's why I propose to meet in a normal environment. But if it's difficult, then forget about it and proceed the way we do. Okay, so I'm stopping my share and see you next week then.